Welcome everyone to another edition of the data science meetup. Today, Pep will be going through machine learning for log analysis. And me and him worked together over the semester on this project, and I think it's pretty cool. It's kind of a subset of the AI for CI work that we're doing in the AI COE as well. And yeah, Pep, take it away.
Okay, thanks. Hi, I'm Pep, and as Michael said, I've been working on this project for this semester, the last one in degree in data science. It's about applying machine learning for log analysis. This presentation is slides I've been preparing for the project's presentation, so I'll welcome your feedback in preparation. And apologies in advance if there's some things. I'll skip things that I believe you probably are not interested in. But anyway, I'll start with basics. So a quick overview of different ingredients in the project. So logs, everybody knows logs more or less, but just to make it clear, they are short messages generated by computing systems as they work to record their own activity, and they are very useful for software developers and system administrators to basically understand what's going on the system. One thing that is relevant to this group especially is that typically, it's hard to find data to work with, but log data is especially tricky because logs tend to contain sensitive information. So there are few sources of logs that can be used as a reference. And there is a team, this research group actually produced a data set of logs that, because there are few others, is kind of a reference in the field for what I have seen. In that sense, the AI for CI project has one of the good things it has is that, working with CI data provides lots of publicly available data, but we will get there. Anyway, those are short excerpts from different sources of logs that are part of that data set and that are commonly used for benchmarking. I will not go into detail. The important part here is to realize that log files across this wide variety of sources, despite their diversity, they all share a few characteristics in general that are common to typical log files. Log files are usually a set of similar messages that get repeated over and over. And those messages are short, just one line, and contain a mix of text and parameters, things that change, things that not change. For example, user Alice logged in, user Bob logged in. And those messages are part of some sort of structure. They come with a timestamp indicating when did this event happen, or a severity level indicating if this is an error, this is a critical problem, or this is just for your information. Those characteristics are important because when we work on trying to analyze those logs, basically everyone tries to optimize based on those assumptions, basically assuming that the logs follow those characteristics. That's it for logs. By the way, any questions, let me know. And I'll skip quickly over CI. Everybody knows what CI is, and I'll skip over what is OpenShift. Everybody knows what OpenShift is, and just to mention that OpenShift has a CI system, OpenShift CI, using Prow. And well, I'll skip over AIOps. Everybody knows what AIOps is. And as Michael mentioned, actually the original idea of this project is the AI for CI project in the AIOps team in the Operate First initiative. So, well, the goal of the project was to apply data science to CI, in particular OpenShift CI, by leveraging natural language processing to analyze log files. And I didn't mention yet natural language processing, but it's important to understand this. My project was in the area of NLP, so NLP was basically a requirement for the project. Okay, well, that's it for the introduction. The project started by looking at the state of the art, what's common in log analysis and automated log analysis, and at a high level, everyone mostly agrees that automated log analysis is a process that has at a high level, two stages. The first one, from raw logs, is to abstract them. ALAT here stands for Automated Log Abstraction Techniques. The idea is to, well, this process is also called log parsing or log abstraction. The idea is to generate a representation, an abstract representation of the log messages that is then used for a downstream task. That could be anomaly detection, failure classification, prediction, or whatever. So this is an illustration of what that initial step, log parsing, where we have a piece of code that generates a log message, and the role of a log parser is to abstract that message and identify the structural elements that I mentioned before. There is a timestamp, a severity level, a component, and most especially an event template. So here you see the example of this file, but it could be from user Alice logged in. So user logged in would be the template, where Alice would be a parameter, right? But in the context of my project, not yet, but just, the review of the state of the art was relatively extensive. Quite a few works were reviewed, but I would point out to those three in particular, which are literature surveys, and basically they directly or indirectly point to all the tools that I've been reviewing. The first two, basically a high-level summary of them is that no one size fits all, meaning that there's multiple options, and you probably should pick the one that works best for you. And along those lines, the third work listed here is by the same team that created that public data set that I mentioned at the beginning, and they did a benchmark of 13 state-of-the-art, let's say, log parsers, and this set up kind of a baseline to analyze performance of log parsers. But now, yes, my interest in particular was to find out which of those works actually relied on a pure natural language processing from the beginning to analyze log parsing. And the results, one of the early findings of the project was that very few, actually, basically almost no one takes this approach of using NLP for log parsing. Having said that, there are a few exceptions, and I would highlight few and exceptions because most of them, again, don't use an NLP approach from the start. But those two works do. I'll not get into the details, but I will highlight two observations from each, well, one from each. The first one, they stress the need of taking a non-supervised approach to this task in the context of this ever-increasing complexity of modern software systems and continuous change that they experiment. It makes it almost impossible to rely on a set of manually created labels that can help potentially supervised task. The second work, actually, they use simple NLP techniques, and they claim that they obtain already good enough results that it makes it not necessary to get fancier. That's it for the overview of the state of the art, and now let's dive into the data itself. And here maybe I will switch from the presentation to the actual notebook that is part of the project. But just let me mention a quick thing. OpenShift CI runs many jobs, and in order to have stable data that allows us to compare results over the course of the work, I picked one of those jobs only. All the data that you will see corresponds to this job, and also each job you will see can have many types of logs, can contain many logs, each job run. So for simplicity, I picked one log that is common, that appears on every job build, which is the build log, and this is where I started. So let me switch to the repo. So the OCPCI analysis repo has a set of notebooks for the different data sources. So one of the data sources is GCS Web, refers to all those logs are stored in a Google Cloud Storage bucket. And those notebooks that I'm showing you here are here. I loaded them before because GitHub sometimes takes some time to render. Can you read this? Well, this is the part of the first of the notebooks. It's about obtaining and exploring and performing an initial exploration of the data that we work with. As mentioned, every job can contain multiple logs, but especially for simplicity, starting with the build log, and also a bit of metadata to be able to work with them. There are a couple of JSON files that indicate when the job started and when did it finish, and the result, basically if it passed or failed. I don't know if maybe if we have time, we can see later what else is there, because there is, once you dive into, so this high level for each job run is basically the same, but once you dive into the artifacts for each job, this is when things start to get complex. But anyway, looking at the general metadata, the first part of this notebook is basically code that can download the data from Google Cloud Storage and generate. Well, it can optionally save a copy of the build log, and in any case, it creates a data frame that contains the metadata. This is again the specific job that was picked up here. The notebook works with any job, but one thing that at the moment, at the time of this writing, so there are two types of, essentially multiple types of jobs of an OpenShift CI on Prow. Actually, you can run jobs on a PR, pre-submit jobs that test on PR changes. The assumptions on those paths here point to only periodic jobs, which they just have a different path in Google Cloud Storage. So it's simple to change, but just keep it in mind. If you try a PR job, it will fail. Anyway, so this is the metadata. Well, basically, very simple feature engineering here, just translating end and start to the duration of the job and filtering out some statuses that are not interesting, in particular error, if Prow itself errors. By the way, I just see another error. There's another state that should be filtered out, which is abort, if the job was aborted. Anyway, but it's very rare. Anyway, most of the jobs either pass or fail, and this is the data set. At the time of that this was written, there were 837 runs of this job. It's good because those jobs, one of the reasons for picking that particular job is you have noticed is 4.8, which is in active development, so that particular job is meant to be run more frequently than others. But they also periodically clean up the history. So, well, anyway, the data set that we had is not huge. So, but at least we had a few hundred occurrences. And this is a summary of the data. You can see that a majority of the jobs run for slightly under 2 hours. And the log size of their build logs is mostly small. Notice that this graph here is in logarithmic scale. So when it's small, it's small, and when it's big, it's huge. But most of them are relatively small. And we had, well, almost half pass fail. The interesting part is when you plot those together, those three together. So this is duration versus log size and colored by pass or fail. You kind of already can observe something. We can see that successful builds are quite homogeneous, and you have those two columns of success here. And then a big chunk of the tests or job runs that fail are here, with a few scattered around the successful builds. The reason why this looks like this is because those again are build logs, and so the log of prow running the job. So I'm going to do this, and when this works correctly, only the steps that the log only contains the steps as they happen. I'm going to install the cluster. Succeeded, and that's the only information you get about the cluster installation. But when things go wrong, the build log includes the content of the failure, messages to help you understand what went wrong, and that's why those failures have such a big build log size. But anyway, one of the conclusions of this is that it would be quite possible to apparently build a simple classifier just based on the metadata, and we would probably have already a significant, it should be possible to achieve high accuracy. Wouldn't make much sense though, because we already have 100% accuracy of pass-fail given by prow itself. That's prow's job actually. So, but that's for the metadata, and here are a few samples of the data itself, so from the logs. And well, maybe for this I will switch back to the presentation because I captured those there as well, and I think they look nicer, but with clickable links and so. Let me go back to the presentation here. This is just a metadata plot that we saw, and let's go into some samples. Okay, this is the full output of a successful build. As you can see, it's one of the short ones. One note here that you can see those lines start with some funny codes. This is the severity level, informational, but info is surrounded by some funny codes. Just wanted to mention that those are ANSI escape sequences that are meant to help in make the output pretty. And here is the prow page for that specific job, and you can see that info here appears in blue, which is nicer to the human eye, but in terms of automated log analysis, it makes it slightly more challenging. Not the end of the world, but well, just to highlight that this is a change. This pretty output is a change that happened recently at the beginning of April during the course of this work. And here is another sample of this is a failed build where you can see lack of capacity. And this is another sample of the same type of failure, lack of capacity. You can see those two logs should be equivalent, and they are, but they look quite similar, quite different, or in terms of actual content due to that change in formatting. The change in formatting also has some other funny tricks that for log parsers can be challenging. Like here, you can see we have each line has 2 timestamps, notice, and notice also how they are different actually, which is fun. And each line also has 2 severity levels, info here at the left all the time, and this column here is the one letter also is a severity level. I stands for information, E for error, W for warning, and you can see they are also different. So also funny for a potential log parser. One final sample. This is another failed build, just a fragment of a failed build, and you can see here that sometimes those build logs contain a wide variety of content. We have some lines that have some structure in the form of timestamps, but some lines that are plain text, and some lines that have some structured output JSON here. Some other outputs have YAML files that take multiple lines. And the reason is that sometimes we see here command execution output, some commands that are not designed to log, but we get the output of their execution in the logs. So to summarize and to compare the characteristics of those logs to the typical log characteristics that I showed at the beginning, those logs are not formed by similar messages that are repeated over and over, and most often they are not always short. Sometimes they take multiple lines. They do contain a mix of text and parameters and other things, and we cannot assume that they contain some structure. Some have timestamps, some don't, some have two. And in short, those logs do not look like the typical input that state-of-the-art log parsers would accept, and also those parsers do not apply NLP anyway. So what to do and how to make the project progress? And here, the key point was to try to find characteristics of those logs that are not common on traditional logs. And because those logs come from CI jobs that start and finish, those logs have a beginning and an end, unlike the typical logs files that, as I mentioned, are treated as a stream of events, one after the other with a continuous stream. Another difference here is that, well, we don't have as much repetition inside of those logs. We have a bit, but not as much as traditional logs. However, each job run is run over and over again. So we have repetition at a higher level, which is log file level. Every job run produces one build log, and those repeat over and over again. So with that in mind, the idea of this project is to treat each log file as a document in NLP terms, and apply NLP at that level, at the document level. Unlike, again, the typical approach to log parsing, which is to apply, to target, let's say, each log entry or log lines, or even smaller granularity. The question is, can this provide additional insight into those job runs beyond pass or fail? And well, here we decided to approach it and try it and try to verify it with a simple technique, simple NLP technique, term frequency, inverse document frequency, or TF-IDF, and non-supervised task of clustering. The idea would be to first model the logs using TF-IDF. The simple technique consists in basically counting words. How many times does this word appear in this document? And this is term frequency. And in how many documents does this word appear? This is inverse document frequency. And the clustering idea is, can we automatically identify groups of job runs in a way that can explain something beyond pass or fail? Okay, so here I'll switch again to the notebooks, and this is where the second notebook comes in. It's loaded here. This notebook does TF-IDF on those logs. The first part basically loads the metadata that was generated at the end. By the way, those are not in a pipeline yet, sorry. I know that there is a way to do it, but those are not saved on an S3 bucket. But it should be relatively simple to adjust. This is the same data frame as before, the metadata frame. You can see the same data. It's just, and this is again the same plot as before of the metadata. And this plot is useful to, it has proven useful, at least to me, as a visual guide of checking if we are going in the right direction or not. And it will be used over and over here to map the clusters, the resulting clusters from the clustering task to that metadata. As a reminder, we have successful builds are those two columns, and the rest are failures. Okay, so, well, before that's a bit of a long run on a relatively important topic, because before we can start to count terms, it's important to understand what a term is. And in, let's say, traditional NLP, a typical term is a word, but here the content of those logs is not written natural language or human language, but it's output of OpenShift CI. So this has been an iterative approach, and you can see it here in commented options of token patterns. Exploring multiple options has led to this token pattern that tries to capture the nature of the content of those logs. Keep in mind that you can have file paths, right? And you can have components that contain dots, or references to images, for example, that have tags, and most especially references to Kubernetes objects, for example, a pod called something like this. But this pod can come from a deployment, let's say, that is, or this comes from a replica set that comes from a deployment, right? So it's kind of hard to distinguish just by looking at the name if this is something that is constant or something that varies. So in log parsing terms, it's hard to find a definition of a term that can easily help us distinguish constant parts from variable parts, especially when you have other things in the logs which are constant, like, or relatively constant, but are actually, they look very similar to things that are different, like the name of a pod. And here is as a side comment, here is where inverse document frequency can help, because by looking at different repetitions of the job, we can identify, okay, we had that same deployment, deployment 3 appears in all those tests, but the name of the pods are different across the job runs. So they must be a variable part, and the name of the deployment must be a constant part. So basically, the idea is let the term capture everything that seems relevant here, and let the model help us detect this difference between constant and variable. Okay, make sense? Well, so with that term token pattern in mind, we did TF-IDF. This is a sample of the vocabulary that resulted, and as you can see, you have things that look like Kubernetes object names, like a service name, or you have normal words, and you have paths, and this is a sample, and things that you do not have. For example, it's important to mention that the first character is must be, in this definition, a letter. So this removes a lot of candidate terms. Anything that starts with a number. Timestamps are not part of that vocabulary at all. If you consider like this one, you will get an order of magnitude more of terms. Anyway, so with that TF-IDF representation, the next step was to try clustering. And again, starting simple, I started with k-means. We'll get to discussions later about k-means maybe. And the simple approach as well, elbow method to find the ideal number of clusters. Here we see an elbow at 3. So the first attempt, let's say, here was to find 3 clusters. So this is the mapping of 3 clusters to the metadata plot that we saw before to help us get an idea of how good those 3 clusters are. And you can see, yes, we have a cluster that seems to have identified the failures here, but with the other 2 clusters have a mix of successful builds and failed builds around them. So this is not a great result, because those 2 groups here are less than ideal. To try to understand why, there are some details about the metrics and the cluster algorithm here, and in particular, this is a plot of the silhouette score. The idea of this metric is to compute how close or far each member of each cluster is to their cluster centroid, and add a score for this. And we can see that the score, the average score, which is a dotted line here, keeps increasing from almost 0.4 here as the number of clusters increases, and it actually keeps increasing. But you can see also that after cluster number 8 clusters, 2 things happen. Some clusters have, obviously clusters become, that's obvious, they become smaller, but also their contents, some of them make less sense, then some of them get closer to other centroids than their own. But in any way, based on this, and by the way, other metrics that were also tried, let me rewind here, a couple of other metrics. We saw the average silhouette score, max out at 8, but couple of other metrics also pointed at 8 as a good, relatively good number. So the next thing to try was 8 clusters, and this is the mapping of 8 clusters to the metadata plot. And yes, correct. Now the groups have separated failed builds and successful builds, but maybe it could be because we are separating too much. The thing is that looking at the details of those groups, it wasn't clear if that separation made much sense. What became clear is that those two columns of truth, let's say, or success, were impacting the clustering task. So the next thing I tried was to avoid that format change. So this change came from a pull request, this pull request here. So the decision was made to drop the logs that from jobs that were run before that PR merged. That left us with a smaller data set, but also apparently much cleaner data set. And this is the updated metadata plot. Now we see no 2 columns of success, just 1, and also quite homogeneous. Okay. Trying with this new data set, the metrics also look more consistent. They all agree that 4 is probably a good number of clusters to have here. So I did clustering with 4 clusters, and this is the result, which actually indeed does look much better than before. There are 2, those failed builds that are scattered here were grouped on their own cluster, and so we have 2 clusters with failed builds, but we also have 2 clusters of successful builds. And why is that? Well, the answer appears when you look at a sample from each group, and notice that this is one of the groups of successful builds, and have some asterisks here that obfuscate actually the cloud provider. This is a sample from the other group where we can see that GCP appears here, where we have asterisks here. So this is an illustration of this iterative approach of finding the best token pattern, or the definition of a term for us. So based on that observation, the next step was to decide, okay, let's include asterisks let's accept asterisks as part of our term definition. Not only that, this time I tried to be, try to apply some domain knowledge, let's say, and instead of being guided by metrics, I said, let's try to make this task identify 3 clusters on the basis that I want to know if this can separate or clearly tell me the successful builds, legitimate test failures, and other failures, let's say infrastructure failures. Okay, so this was purposely forced to try clustering with 3 clusters, and yes, this kind of worked, which was great. We can see that this managed to correctly identify 3 clusters that made sense. So this was already a happy result, I believe. But then it doesn't hurt to look at the metrics, right? So this continued by actually plotting the metrics again and realizing that the metrics suggest, hey, Pep, why don't you try with 5? It has a smaller elbow here as well, and the other metrics look better. So okay, let's try with 5. And trying with 5 provides those 5 clusters, which also look quite good. It essentially has divided the 2, so the successful builds in the 2 groups that we saw before. Again, yes, we have here, you see a list of the top terms in each cluster. You can see that there is cluster 3 that still has groups the builds that have obfuscation, but now we see that in the list of terms, and when we know why, this is the other successful build. And we can see that just by looking at the list of terms, we can see that the 3 failure groups, this one is legitimate failures, which we see things like seek storage. This is tests that have failed. So this is the group, the blue group here. Here we see failed to acquire leases. So here PROW failed, and we have the group of failures caused by PROW itself, and the final group is failures that happen on the preparatory steps of it failed not because of PROW, but because the cluster installation failed, for example, and it couldn't run the tests. So all in all, basically in summary, and here maybe I will, this is just the rest of the notebook only shows a sample of each log, and at this point I'll go back to the presentation because I notice that time is flying. Apologies, but let me jump to the conclusions here. Or oops, pretty much. Well, the summary of this part is that by using this approach of treating entire log files as documents and applying a simple NLP technique, we did manage to obtain insight into CI job runs. And we also learned that, well, picking a token pattern has an impact, and also the format change in the output of build logs had an impact. Okay. I have more, but I have a question. I have a doubt if I should continue or pause here for questions or comments. Should I continue? Silence,
yeah.
everyone.
Does anybody have any questions?
Okay, it will be short. It's not much more. But the question was now: can we improve this, this dependency in the token pattern and reduce the impact of the format change? And to do this, and also to try alternative NLP approaches. Another thing I tried was, and this is not yet on a notebook that has been published. I have it in a draft mode here. I can show it to you here, but I basically tried more sophisticated NLP technique based on word embeddings, actually at a higher level, document embeddings, doc2peg. One encouraging thing is that the two references that I mentioned at the beginning, the only two that use NLP for log parsing, the first of them actually uses that approach, actually word embeddings, or basically they highlight that anything based on, well, not anything, but their approach based on neural networks is much more resilient to the choice of a token pattern. Actually, they suggest to use just words, standard, the default tokenizer of plain words. They actually don't do it. They also use a bit of domain knowledge and accept, square brackets for Apache logs or something like that. But they essentially claim that this type of approach should be more resilient. Let me show you maybe the notebook that I have in the works here, and this one is much less polished and it doesn't have comments like text comments yet. Sorry, but anyway, the first part is the same as before. Oh, notice that I don't clean it. So for this exercise, I don't remove the old logs. So try with a dirty log file. And by the way, this was also refreshed. It's we have, this was run later and has a few more runs, a few more 100 runs. And also the token pattern is much more generic. Actually, any alphanumeric string of at least 2 characters, right? So the goal here is, can this provide more resilience or more independence? Well, I'm not running it live because I don't have a GPU and it takes a while here. But this is the type of result that you can see here, that we have terms that now we have timestamps divided, by punctuation characters, but we do have numbers. So the vocabulary is much bigger. This is a full log file, by the way, tokenized by this token pattern. This is clearly a successful build. but you can almost read the full log file here. And you can see, well, succeeded after, well, yeah, 4 minutes is only the provision. Okay, anyway, this is the full log. So how this looks like? Well, by the way, there are some other considerations here that we discussed, which is we're working with vector representations that have a high number of dimensions. This doc2vec, I'm using word vectors of 100 dimensions. But remember, TF-IDF, we had a resulting vocabulary of over 4,000, meaning that each document was represented by a vector of 4,000 dimensions. So there are known issues when working on those high number of dimensions, especially when you use a metric distance based, like using the Euclidean distance. In short, from that point of view, it's hard to see how the previous exercise worked so well. So we wanted to explore other approaches here, and in particular, starting by reducing dimensionality using, in this case, TSNE. This is a representation of the vectors using TSNE, and we see those there seem to be 3 groups here, and actually there's an attempt. Well, K-means at least manages to identify them, and this is a plot about the metadata. It kind of works. We have some of the same problems that we saw at the beginning with the initial attempt using K-means in the TF-IDF approach, and slightly better results actually, because some of those are actually identified as failures, but still some problems with this. And a similar result is obtained while working with the, or a relatively similar result. By the way, I refreshed this morning, and it doesn't look as nicer as it did before refreshing. But working without reducing the dimensionality provides essentially similar results. Not here, but I can tell you that optimizing DBScan a bit, we can get the similar results as the 3 clusters here with the dimensionality reduction. But none of the tests using this method provided as good results as the ones obtained by TF-IDF. However, remember that maybe the highlight of this is that we are using a much simpler and domain independent, if you want, approach of a generic token pattern here that doesn't depend on well, crafting the token pattern. And let me conclude with let me just show some final conclusions here. To summarize, again, I think that the work proved that CI log analysis can be done successfully with NLP, and TF-IDF already shows some promising results. And this ongoing experiment with more sophisticated approaches suggests that we can provide additional robustness. This is where I am right now. I think it opens the door for future work. Like, if the TF-IDF work results are so promising, maybe it's worth trying to productize them and put them to work, and see if they can help on day-to-day observations in OpenShift CI. Another interesting next step would be, okay, this was build logs, but there's much more in OpenShift CI log data. Maybe focus on some specific actual CI output, like test output, and see if that provides better results, especially for doc2vec, and also especially for doc2vec, using more data would be like, we have been working with one job. doc2vec can benefit from more data. And in diving into specific CI job and also in applying, productizing this, recommendation would be involve subject matter experts, people who work day to day with OpenShift CI and get their advice on where to focus. And basically that's it. That's what I have.